Okay folks, we're back here again at the motor, and what I thought I'd just run through today was the stainless steel end cap that we have on the motor that I got made up. This is made from 1.2mm stainless. And I've been very fortunate this time around with the metalwork angle of the project. A good friend of mine put me in touch with a very good metalwork company that don't seem to have a problem doing small one-off custom work. It's not overly expensive, and it only takes a couple of days from one of my rather poor quality hand-drawn sketch to getting something that really is first class quality. So I think it's going to make things better, both from a physical and an aesthetic point of view this time around. So anyway, the disc is stepped up by 20mm going around the side, and we located 4 M6 Allen head screws to bolt it onto the back of the motor frame, because this particular motor, as you may recall, had an open commutator end plate that just had a mesh screen on it in the original application. So we've taken that away and sealed this off now with the stainless end cap. We have our blower inlets here, which we'll be utilising for cooling. So one of the other things that I've managed to make happen here with the end cap is the RPM pickup. I thought that we'd talk a little bit about that, just how to kind of easily generate an RPM signal from a motor that has no tail shaft, as unfortunately a lot of these motors don't come with that facility. So in this case, what I did was, when I had the end cap off the actual motor during the rebuild, I drilled out the end cap so that it gave me access to the shaft face and the actual face of the bearing on the commutator end. And the purpose of this was to basically facilitate my being able to arrange for a Tach pickup to be applied to the motor. Now it's similar in a way to what I did on the E36, but I think it's a little bit better. What I did on the E36 was that I used two little stainless steel pieces of stainless round bar, just some 6mm diameter round stainless, about 5 or 6mm long, and I epoxied them using some fast setting epoxy compound onto the face of the commutator end bearing. And that is exactly what we've done here. We just did this today actually, so I'll try and get a closer view on that. Got my phone cable tied to a camera tripod here, so we might have a bit of less shake in the situation. Don't want to be doing the shake and vac all the time. The last couple of videos were, shall we say, something on the Blair Witch kind of a situation. So what I did today is I came along here and just epoxied on, as we can see, just two M6 stainless steel nuts onto the face of the end shaft, and done in such a way as that there's two of them approximately 180 degrees apart, for the purposes of generating 2 pulses per revolution, which would be for normally a 4-cylinder engine, but that's what the that's what the software in the controller is looking for. So that's what we've stuck with in this case. And the advantage of the fact that we're going to be using software in the Arduino to take these 2 pulses per revolution and feed those into a bit of code that generates the 58 pulse and the 2 missing pulses from the E39 reluctor wheel crankshaft position sensor, means that we have that amount of flexibility in our design. But if we needed 3 pulses for a 6-cylinder engine, we could come along and just space the nuts into a 120 degree position, and if we needed 4 pulses for a V8, we could just put in 2 more, so we'd have 4 pulses per revolution. So then what we do is we need something to detect that. So I use one of these Omron threaded proximity sensors. This particular one is an NPN sensor. It runs from 10 to 32 volts DC, has a little orange LED in here when it's triggered on. It's a basic NPN system in there, so I'll go through that when we're doing the Arduino interface for the Tach and all that stuff. But it's basically M12 threaded, and what I did here was threaded the thing in and just epoxied the inside nut, so that allows me to screw the sensor in and out of the plate here without having to take the whole thing off and then hold this with a pliers or a spanner and then retighten. So it just vastly improves the situation. So what we then find is that when we put our cover back on, I'm trying to do this one-handed here now for some reason. We reattach the cover. Obviously the whole position here is drilled in such a way that it lets the sensor read the 2 nuts as they pass by the front of it, and that causes it to trigger the NPN transistor, so you can then just put a resistor to supply voltage, and you can just come along then with whatever kind of a signal shaping circuit that you require to drive the end application. But this is a kind of a trivial and easy way to obtain an RPM signal from a motor that doesn't have a tail shaft on it, and it can really be used with almost any motor. It just needs a little bit of basic machining. It's nothing that one couldn't actually do with just a hand drill or a drill press. So that's back on, and what we'll do is I've just got a 12 volt power supply here, and we'll connect that up. We got it connected up here, sorry, to the sensor. So when I turn it on, you can see it's drawing a small amount of power, and when I move the motor to, just going to move the motor, just a little piece of wood here just in the drive end, just to move it around, and we can see there that there's an orange LED after illuminating on the base of the sensor, and that tells me that the sensor has detected one of the nuts that's just passed into its detection range, and the current on the power supply has just increased to 6 milliamps. So if we continue to rotate the motor, once the nut goes out of the detection range, the LED goes off. And if we continue to rotate, bring the motor around to the next nut. As we come into the detection range, the LED comes on. So that's really how our RPM sensing is going to be handled for this particular motor, and it's how we're going to ultimately seal off the end plate, provide cooling air, and that's about it. In terms of the motor, it's almost ready to go into the car. Just have to finish tigging these pipes in here and clean them up a little bit. It's a bit of a bore in there where they were cut, so I want to get all that cleaned up before it goes on there finally. And let's see, what else do we have to do then? That's about it really. I've got the exhaust and all of the other bits out of the car. I was able to measure the drive shaft, and my idea of going with the automatic version of the drive shaft seems to have played out, because it's 160 mil shorter than the manual, so that lets me move the entire drivetrain backwards by 160 mil, so it'll let this end of the motor miss the steering rack and give me a bit more space as well. So that'll be the next part of the plan. So yeah, that's about it. Just thought I'd run through the Tach sensor setup and how it's actually done. It's all fairly straightforward, but this can be pretty much duplicated for any motor that's been repurposed for an EV traction application. Okay folks, talk to you soon.